Then start the presentation.
Okay, so let's start. Hello, everyone. Welcome to the Zephyr Developer Summit. It seems that it's the very first presentation of the day, right? Of the first day. So thanks for having me. My name is Flavio Seolin. I'm software engineer at Intel and the current power management maintainer. I've been involved. Oh, it's echoing. Okay, now it's better. So yeah, let me continue. I've been involved on Zephyr for more than two years now, and the other areas where I contribute most are security and safety.
Flavio, real quick, do you prefer questions at the end, or would you like questions throughout if people have them?
They can interrupt me at any moment. I think it's better to answer the questions during the presentation than left to the end.
Okay, so yeah, if you have a question, you can put it in the chat or use the raise hand and I'll unmute you so you can ask your question.
Okay, and Brett, will you let me know if any question arrives, or should I pay attention on this?
Flavio, I'll try to keep an eye on the chat window.
Okay, perfect. So before we start, what is power management? If you don't know anything about this topic, you just start and look at the Wikipedia and we will find power management. It's a feature that turns off the power or switches the system to a low power state when inactive. That it's a very straightforward statement and resumes well what it is. Basically, if there is something that you are not using or is not needed, just turn it off. We do this all the time in our lives, right? We turn off the lights when we no longer need them, or we turn off the faucet after we clean our hands. There are many examples, but why we do it? We can list some reasons here: to save money, to reduce the impact in the environment, to prolong the product lifespan. In case of an embedded system, we may add to prolong the battery life. Imagine devices that are left unmaintained in place of difficult access for months. It's crucial that you extend the battery as much as possible to reduce read dissipation and noise. And certainly there are several other reasons to do power management. Okay, now the big question is how Zephyr approaches this problem. Trying to answer this question, I've divided this talk in the following sections. First, I will start with the goals because they ultimately drive the architecture and features that we develop. Then I will move to the main topic, that is how power management is implemented on Zephyr, explaining system power management and device power management, trying to go in some details about them. After that, how to enable power management from the perspective of someone that just want to use it in their application, and from the perspective of someone that wants to implement power management in a new SoC, a new driver, or customize everything in their application. Finally, we have some conclusions. Let me just add a disclaimer here. I will not cover any particular target in this talk. This is all about the power management architecture and how it interacts with other Zephyr components. Okay, moving on, the goals. First, consume as little as power as possible for a given use case and configuration, and don't waste energy when the system is idle. But which use case and configurations we are talking. It would be a lot of pretension or ingenuity from our part if we said that we know all of them. We certainly don't know all possible use case and configuration. So deriving from this, we have the second goal. The subsystem, the implementation has to be customizable. Applications have to be able to tune the system according with their needs. Zephyr has to provide the mechanisms and not the policy. It also has to be cross-platform. It has to support different architectures, boards, SoCs. The ecosystem, it's very big. Last, but definitely not least, it's crucial it be convenient to use and deploy. Power management, it's a shared effort. We need device drivers adopting it, architectures supporting, and applications customizing according with their needs. Now that the scene is set, let's see how Zephyr attempts to achieve these goals. To try to answer this question, first, it is important to understand where power management sits in the overall Zephyr architecture. This is it's a very well-known common diagram with Zephyr components. You see this equivalent picture a lot around the documentation and probably in other presentations. As you can see, they are grouped in three major sections. On top, just below the application, we have application services that contains high-level protocols, APIs, and services. Just below that, we have OS services. There we have drivers, APIs, some functionalities like IPC, logging, file system, and also some low-level APIs, network protocols, and device management that allows remote management and is based on the simple management protocol from MCU, but among other components, of course. Finally, we have the kernel. And as you can see, is there where the power management sits between the platform and the scheduler and other kernel services. Although most of the power management code lives in its own subsystem out of the kernel, it makes sense to put power management here because the kernel, most specifically the scheduler, is the main power management governor. The kernel knows when the system needs idle, when the next event will happen, and consequently when is the right time to do power management. Okay, so some key concepts. First, kernel idling. This is where most of the magic happens, at least for the system and central device power management. Kernel idling, as we are going to see later, is basically a code that it's executed every time the system has nothing to do because all the threads are blocked waiting for some condition. It is in this code that the power management it's hooked. Then we logically split the subsystem into two major areas, system power management and device power management. System power management is governed by the idle thread, as I mentioned before, and it's responsible to save energy changing the SoC power state. Power state can also be called idle state or sleep state, depending on the document that you read. So the term is interchangeable, but on Zephyr, we mostly use power state to designate it. Two important components of the system power management are the policy manager and power state constraint. The former is responsible to tell the subsystem which state should be used. This can be considered the brain of the subsystem, is the code that will decide based on certain conditions which power state brings more benefit for the application. We are going to see later how the default policy on Zephyr works and how applications can define their own policy. Power constraints, as the name suggests, are constraints setting power states that will inhibit the system of using these power states, a specific power state. The other major area is device power management, that it's responsible to save energy suspending devices or putting devices in low power. Device power management can be central and runtime, or also it's called dynamic device power management. Central happens when the system power management, depending on the state that is transitioning, suspend or resume the devices. And runtime, on the other hand, it's more ad hoc process. Devices can get or release reference for other devices that they are using, and when no one needs to reference a specific device, it's automatically suspended. For example, you have a UART gets a reference for a GPIO driver, and when it needs to use it, and release when they no longer need it. If no one else is using GPIO, the GPIO driver will automatically be suspended. This runtime or dynamic device power management, this dynamic behavior, it's called runtime power management on Zephyr. Okay, let me move to the next slide here. I need to. Okay. Okay. Now that we have an idea where power management fits in the Zephyr architecture, and we talked about its key concepts, let's focus in the subsystem architecture. If you remember in the previous diagram, we put power management within the kernel as if it was only accessed there, but that was not completely true. I mean, it is true that the power management is triggered by the idle thread, and that this subsystem talks directly with device drivers and the SoC layer, but it also exposes APIs and interacts with applications, the power subsystem. One API that I have already mentioned is the power state constraints. Applications can inhibit the system of going to a particular state. Actually, they can inhibit all the states, and the system will always be active if they want, of course. Also, applications can use certain API to receive notifications when the system changes states. There is another one that applications can use to bypass the system policy and the idle thread too. It is an API that an application can use to change the system power state immediately. This API is especially useful when Zephyr is used as part of a bigger platform, and the power management it's controlled by another SoC, another OS, and by IPC. You need to shut off or to power off Zephyr. Okay, the next slides I will cover the system power management. In order to understand system power management, we have to take a step back first and talk a little bit about the scheduler and the idle thread. I have referenced the idle thread several times now and said that it is the governor of the system power management. But what exactly is the idle thread? Zephyr scheduler, it's a priority-based scheduler with optional round robin and time slicing. This means that the scheduler will always schedule first the threads with high priority. So for example, in this diagram, the scheduler will schedule thread A. Then when this thread reaches what it's called a reschedule point, finishes or reaches a reschedule point that can be, for instance, caused by waiting on a semaphore or yielding or sleep, the thread is then marked suspended or waiting, and the next thread will be scheduled. Finally, when all the threads are suspended or waiting, the scheduler will schedule this special thread called idle thread. Idle thread, it's a thread that it's created with the lowest priority in the system. It's here where system power management happens. The idle thread, it's basically a loop that every iteration does power management calling the power subsystem, and if no action is taken, just wait on an event. If no other thread is ready to run, this thread will be scheduled again. Just a side note about time slicing here and the round robin feature. The kernel does not distinguish if the next programmed event is due time slicing or not. So the first time the idle thread runs, it may have an event that already scheduled, and consequently the time idle will be lower than application would expect if it was, calling something like sleep or something like that. The times and it's important to know that the time slice is not renewed if there is no thread ready to run, and the thread, and when the scheduler schedule the idle thread. Okay, so let's take a look inside the idle thread. The idle thread, it's a continuous loop that, as I said, each interaction first locks IRQs to avoid being preempted during its logic. Then checks if the target was built with power management support. If it was not, that it's the simplest path. Then the idle thread just calls an architecture or a specific implementation to put the CPU idle. For example, on ARM, it sets the premask to 1, configure base priority, and then wait for interruption. On x86, it enables interruptions and halts the CPU. And then when interruptions arrive, the CPU awakes, and this loop continues until another thread is ready to run. Now, if the system supports power management, the idle thread calls the power subsystem, passing or giving the power subsystem the number of ticks for the next scheduled event. At this point, we are finally inside the power subsystem. The first thing done there is to call the policy manager to know which state we should use based on that number of ticks. Based on the state returned by the policy manager, we may suspend or put in low power mode the devices. After we have done this, after we have done the operations on device, we ask the SOC layer to go to the given state returned by the policy manager. It is important to note here that interruptions are locked, so the SOC has to account these and configure a way to wake up and not sleep forever. When finally the system wakes, caused by the interruption, that could be, just by a timeout, a program timeout, or a external interruption. The power subsystem, then we resume the device. We return from the SOC call. Then we resume the devices, and we call this function that it's also hooked in the SOC with the pause. It's a callback for the pause operations. When this callback finally returns, it's expected by the system that the IRQs are restored. One note about this diagram, the blocks on solid gray are part of the device power management. If the application is built without device power management support, these steps can be skipped, but the rest of the flow in this diagram, it's exactly the same.
Sorry, do you mind a question?
Yeah, sure, you can, please.
So in the previous graph, you had this IRQ lock.
Mm-hmm.
Do you mind explaining that? Like, doesn't seem to have missed the corresponding IRQ unlock. So
yeah,
that's IRQ lock.
Yeah, it's kind of a weird API, but we lock the IRQs when we started the idle thread, the power subsystem logic. When the subsystem needs, when we don't have support for power system, we just call the CPU idle, and this CPU idle automatically releases or unmasks the calls the corresponding to IRQ lock, so he restores the IRQs. When the power subsystem is enabled, it's responsibility of the SOC to restore the IRQ. So,
so when you enter the low power state, the IRQs are re-enabled, right? Or
when you actually you have to program. You have to block almost all the interruptions, because you don't want to be interrupted for something when you are sleeping. You have to configure a interruption to awake and mask probably the others. It's basically up to the SOC to set up this. We call the SOC with the IRQs locked, so they can do whatever they need. And when it finishes, it's expected by the kernel that the IRQs will be unlocked at this point. So it's it's responsibility of the IRQs to unlock the IRQs.
Okay, I understand.
Yeah, the main reason is because we don't want to preempt or to interrupt the SOC with interruptions during the when they are preparing to sleep or something like that. So they are called with the IRQs locked, and they do whatever they need. And when they after they sleep, the system expects that they restore the IRQ.
Okay, but the app developer, the app developer is still sort of in control over what interrupts will wake the system, I'm guessing, right? Or
they can't. Actually they have to configure this.
Okay, so it's not. Yeah, I was just wondering, like, if it's a very hard coded per SOC or.
No, yeah, it's not.
Thanks.
Yeah, sure.
Flavio, there's also a question in the chat. How does it work with IRQs expected by drivers while system is idle? If KCPU idle aware of enabled drivers expecting IRQs and does not enter power saving in such conditions?
Okay, let me open the chat because I'm
sure.
Just 1 second. The question is big. Where can I see the chat here?
Show conversation is what you're looking for.
Yeah, I'm saying, okay, how does it work with IRQ expected by drivers while system? Oh yeah, yeah, the CPU idle, it's aware of the drivers. Actually, we just wait for. We don't mask all the interruptions. We allow interruptions to come and wake the system when the CPU is idle, and then we just don't answer the interruptions at that moment. We return to the power subsystem, and then the IRQ is dispatched. So the CPU idle, it's aware and about the interruption.
Okay, and I have a follow-up question. Actually, the question from the chat was mine. So if CPU idle is aware of the drivers, is it aware which power states are allowed at the drivers in given driver state? I mean, the drivers could have some restrictions like CPU IRQ latency, right? Or CPU latency when handling IRQs. So depending on the sleep level, the latency increases. And is this KCPU idle aware what is allowed latency by each driver to make sure that it doesn't enter too deep sleep for the active drivers?
Oh yeah, so let me be clear. The KCPU idle, it's called only when the power management, it's the SoC doesn't implement a power management. So you are not going to a deep sleep state. You are just sitting waiting for an event with the CPU idle. So you are not going to the sleep state. The sleep state, it's only you just transition into a sleep state when the power management is enabled, and the SoC, it's the hook in the SoC, it's called. And at that point, it's expected that the SoC knows about, or the platform knows about the drivers and whatever they need to do.
Okay, so do I understand correctly that this CPU idle just enters the lightest possible sleep state?
Yeah, in the case of the ARM, is just invokes the waiting for interruption, and or in case of the x86 is just STI and then halts the system, and any interruption that arrives will wake up the CPU.
Okay, I understand. Thanks for clarification.
Sure.
Actually, can I carry on? Another question. I seem to just regarding wake up. Like it was a while ago since I did anything with the PM system. It was 1.4, I believe, and I seem to recall that basically anything would wake the system fully in that back in 1.4. Like an interrupt comes and then the system wakes up fully. Is it still like that, or is that changed now? Or
if you are using the CPU idle, yes, any interruption will.
Yeah. Okay. Yeah. Sorry. I think Yeah. Okay. So it's SoC specific essentially is what it. If you do. Okay. Yeah. Okay. Good.
Okay, so let's continue. So so far I've talked several times about the policy manager, and that this is responsible to return the power state that will be used by the subsystem. Let's now look how they look like. First, power states. The states are inspired by CPI states. We have 7 states if we count the one when the system is active. So states go from active, where the system is fully powered, to soft off, that it's the deepest sleep state available, the one that consumes the minimal amount of power. Of course, as deep is the state in this list, more is the energy saved, but there are certain implications as well, like, for example, memory retention, if devices need to be suspended, and the time required to the system wake up. I recommend anyone that it's interested in this to take a look in the documentation. We have documented what is expected from each state and what is the CPI related relationship as well. Platforms, SoCs should map their states to these ones. Obviously, in most cases, they don't have all these states, and it's fine. They need to declare only the ones that they apply to them to do this map. There may be certain cases where a target has 2 sleep states that would map to one Zephyr state, for instance. In these circumstances, they can use a substate ID to make these distinctions. States should be declared in the device tree to be accessible by other components like the policy manager, more specifically by the policy manager. On the right, we have the full representation of a power state. besides the state itself, we have other two properties that are mean residence that tell us the minimum time that the system should stay idle to the state be worthwhile energy-wise speaking. And the exit latency, that it's the amount of time required to the system exit the state and become active again. This is used by the subsystem to program the timer in a way that the system does not miss a schedule event. Okay, we talked about the states. Now let's talk about the policy manager. The policy manager is actually quite simple. It's just one function that it's called from the power subsystem with a specific number of ticks to the next schedule event. And based on this, it has to return which I state from the ones available in the target that the system should use. Applications can define their own policy, just defining this function, or they can also use one provided by Zephyr. Currently, we have two implementations. One that it's a dummy implementation that just iterates over the available states, and it's used only for test purpose. And we have also the residence policy that it's the full own system. The residence policy looks the time to the next event and then selects the deepest available state that don't have a constraint and the minimal residence is lesser than the time to the next event. Okay, some extra notes about the system power management before we move to device power management. Applications can set constraints in power states to inhibit the system to go to a particular state, or they can do this for a particular, or they can do even for all states and keep the system active all the time. Devices are suspended and resumed sequentially and synchronous. So that it's something that we need to look in the future. The time spent to a device's sleep is not being accounted in this process right now. There are APIs to set and unset devices busy. So devices that are marked as busy are not suspended by the system. And as I talked before, the power subsystem uses the exit latency information in the power state to ensure that the timer is programmed properly and it's accounting the time required the system return to active state. Applications can register to receive notifications about power state changes. And finally, is responsibility of the application to set up a wake up event.
Yeah, just doing it one more time.
Okay. Okay, so let's talk.
Looks like there's a question from Hubert.
Yes, I'm a little confused right now. Is this policy taken into account by the idle thread, or is it separated mechanism?
Oh, the policy, it's called by the power subsystem that it's triggered by the idle thread. So let me go back to the diagram to make this clear here. Okay, as you can see, you have the idle thread. That it's the diagram for the idle thread. When power management is enabled, the first thing that the loop does, it's called the PM policy next state. That it's here. It's the policy manager. The policy manager will check. Okay, that it's the number of ticks. It's the number that I can sleep right now. It's the time is scheduled for the next event. So based on this, what is the best state that the system should go to save energy? So the policy, it's called by essentially by the idle thread.
Okay, so
in the idle thread loop.
It is possible that this idle thread loop finds out that the next event is scheduled, I don't know, in an hour in the future, and it decides to, for example, suspend to RAM, right? To meet current policy. Is it possible?
It is.
But okay. However, the system could meantime expect asynchronous event. For example, UART is enabled, and it can get UART interrupt at any time. And for this given system, UART might have to respond to this UART in limited time. So how is it handled? How this power management policy know that there is running UART driver and this UART driver needs latency no more than, and because of that, it cannot go to suspend to RAM, but to some lighter sleep.
Okay, so in the policy that it's provided by Zephyr, these residency policies, there is no way to know this. So you can write the policy or put a constraint in, if you have this possibility to that you receive a event on UART and you can go to a very deep sleep state because the time required to wake up would be greater than you have to answer the interruption, then you have to set a constraint and not go to that state.
And the constraint is set by the application or compile time? How could I do that?
Oh, you can. It's done by the application. Applications can set.
But drivers cannot do that directly, right?
Oh, drivers can do this as well. Drivers can
Okay.
set any component on the system can set constraints.
Okay, so the drivers could be aware of the power management policy and set it accordingly to make sure that latency is not greater than the driver expects, right?
Yep.
Okay, perfect. Thank you.
Okay, so let's now talk about the other major area in power management, that it's the device power management. Okay, some key concepts for device power management. First, we divide device power management into two categories, central and runtime, or also called dynamic, as I've mentioned before. Central, we have talked early, and happens when the power subsystem suspend the devices when changing the SOC power state. And runtime is the capability of suspend or resume devices automatically according with their usage, independently of the system power management. We are going to see these in more details in the next slide. Devices are suspended and resumed according with their dependencies. So this means that the system does not suspend a device while there is another one depending on it. Drivers maintain power states per device, and to support power management drivers, drivers need to implement the power management interface that it's kind of IO control style API with commands to get and set state. I've already covered central device during the power management section, during the system power management section. Let's just recap this. When the idle thread runs, it calls PM system suspend, the power subsystem then calls the policy manager, and then depending on the state returns, the system can do device power management. If the state selected is suspended, then devices are suspended. If the state is selected, it's either idle or standby, then devices are put in a low power state. These operations are done calling PM device state set, that is just an interface for that IO control style API defined by the driver. In the bottom of this slide, there is a list of the device power states. In this logic, we that it's shown in the diagram, we just use the active, low power, and suspend. Resuming and suspending are used by the runtime power management, the runtime device power management in the asynchronous operations. Okay, so now let's see device runtime power management. These features, this feature allows the application, or actually any component in the system, deal directly with device power management. This saves power even when the CPU is active. Allows save power even when the CPU is active. This diagram gives us a glance of how it works. In this hypothetical scenario, we have an application and 3 devices. The application opens the device A that depends on device B. So the device A calls PM device get that activates device B, assuming, of course, that this was previously suspended. At this point, the internal usage count of device B is 1. Then the application use the device A, calling some methods there. While this happens, the third device C, also requires device B and calls PM device get. And at this point, device B usage count would be 2. Finally, the application closes device A that consequently no longer needs device B. So device A calls device PM device put. This will decrease the usage count of the device B, that now it's 1. In this scenario, device B is kept active because device is still using it. But when device C stops using it, will call and calls PM device put, device B will automatically be suspended because the usage count will reach 0. Oh, yeah, so I saw the question. No, Zephyr right now does not support frequency scaling. I mean, yeah, right now we don't have this. Okay, so moving on now, the final part of this, to the final part of the talk, that it's how to use and enable power management. Okay, beginning with how to use power management. There are 3 symbols that control power management features on Zephyr. The first one is PM, that config PM, that it's the symbol that enables system power management. Then we have PM device that enables the infrastructure for on devices to do power management. If this option is enabled, and also PM it's also enabled, we already have the central device power management. The last one is PM device runtime, that enables, as the name suggests, runtime device power management. This option depends on PM device to work, because the runtime API calls the interface defined by the device, only that it's implemented only one PM device it's enabled. All these options are accessible through kconfig. But it's worth to mention that all these options can be used together. So it's totally okay to have central and runtime device power management enabled at the same time. Okay, so let me see the question. I think that we have. Okay, so let me try to answer this question. PM device enables the device power management on Zephyr on devices. When this option it's enabled, the system can call and can ask a device to change its state. The device runtime it's another API to do the dynamic device power management, and this device runtime API calls or uses this interface defined by when you have PM device enabled. Drivers that wants to use the runtime API to when they want to express these dependencies with other devices, the code has to have PM runtime device enabled. So they are kind of complementary API. So the device runtime requires the PM device, and the PM device it's the minimum implementation to support device power management. Okay, so continue now implementing the SoC layer. That, if you remember, it's the code called by the power subsystem to change the CPU state. You should implement it if you are porting a new SoC or if your application wants to override the implementation that comes on the Zephyr code base. These APIs are defined as weak symbols, so the application can define their own version that will take precedence over the Zephyr implementation. So in resume, what should be done? Implement these two functions and ensure that the power states are defined in device tree if you want to use the policy manager provided by Zephyr. One side note here, define the states using the device tree is the best approach because, as I mentioned, that it's how the policy manager provided by Zephyr access the available states. But if you are defining your own policy that know this information, you don't need you don't really need to implement the states on the device tree because the states are basically consumed by the policy and by the SoC. So if you are having your own customized solution, you can just define your policy, and that the state that your policy returns will be passed to the SoC. And as you are providing the whole solution, you should be aware of the states that you implement. Another thing is to remember to have the interruptions restored after PM power state exit post operation callback returns. So at the end of the code executed by the SoC, when it returns to the idle thread, it's responsibility of the SoC layer to restore the interruptions.
Flavio, I just want to note you've got about 10 minutes left in the session.
Yeah, okay. Yeah, I'm almost finishing. I think I have just a couple of slides left. Okay, so implementing the power management on device that want to support device power management just need to implement that IO control alike function that I have mentioned before, and they can do this passing the function name to the macro that it's used to define a device, as you can see here. On the right of this slide, you can see a simple implementation of this function. It receives a command that can be get or set the state and a callback to notify when the operation is concluded. I forgot to mention, but this API can be asynchronous. If this function is implemented, the driver automatically will support central and runtime device power management. It's just necessary to enable these options when building Zephyr. The last component in the power management that applications can replace is the policy manager. Applications that want to use their own custom policy just need to define the function PM policy next state. It's also defined as a weak symbol, so the application just need to define this function if they want to use their own version. And as mentioned, the state returned by the policy will be used by the system power management to figure out if devices have to be suspend or low powered, and then will be passed directly to the SOC layer. Another thing, we provided several macros to extract from the device tree informations about the supported power state. So if these information about which power states are implemented or supported by SOC can be easily extracted from the device tree if you are writing your policy manager using certain macros that are provided by this API. Okay, so it was covered power subsystem architecture, system and device power management, and how to implement and use them. Now let's go to some conclusions. So power management on Zephyr, it's extremely flexible. Applications can change every single bit of this according with their need. It is possible to customize power states using device tree overlay, for instance. The policy manager can be completely replaced or tuned using constraints. The SOC implementation can be overwritten. Device power management and system power management can work independently, and it can be enabled or disabled. It is indeed a cross-platform, and the architecture looks robust and flexible enough to support multiple devices. Oh, sorry, what happened? So the question is, can you hook SOC implementation rather than override? What do you mean with hook? I mean, just one of the SOC layer is just two functions that you have to implement. You don't need to, if you already have a full implementation for the SOC that we are using, you can just replace one of these functions, but they are not, you cannot compose them. So I don't know if that answered the question. So either you re-implement the function that it's called by this power subsystem. You don't need to implement both functions. You can implement one of them if you want, but they are not composed. It's not like you can just hook something that will be called after the SOC, the full SOC implementation. Okay. And yeah, it seems to offers great power savings, suspending device at runtime and sleeping the SOC when the system needs idle. Although just few devices currently support power management on Zephyr. I have one. This picture was captured using the blink sample on the STM32L562 board with all the power management components enabled. As you can see, the power consumption was very predictable, keeping it very low, just spiking when the LED is blinking. The software that I used to capture this data was the STM32 cube monitor, but other targets have similar tooling and they are very useful. Nordic has one called Power Profile Kit that you can use with Nordic targets to do power profiling and all this stuff. It's very cool, and you can use when you are developing and testing. To finish, I want to ask everybody here to join us in the Slack and to engage on the power management development on Zephyr. The implementation has changed a lot during the last releases, and now we are going to have it more widely used, I hope, and probably we start finding the problems and the things to change. And that is it. Thank you very much for attending this presentation. I really appreciate everyone that attended.
Are there any questions that people have for Flavio before we end the session? Okay, well, thanks so much, Flavio. Great presentation on power management. I'm going to go ahead and stop the recording, and then I need to hop over to the USB session.
Okay, thank you, everyone.